Okay, maybe we start, yeah. 10:50. I don't want to take your long time, but just try to do some of the problems with you guys, yeah. So you know few things, and then it will be easier. It's not hard thing, just a basic conceptual understanding, and then that's it. Okay, so let's share the computer screen of recorded. Yeah, that's good. Okay, so what we did. Oh, not this one. So what we did. Okay, that's the problem we solved, right? Of course, if you want to try to write everything, it may take very long time. Yeah. But if you understand and just draw the pressure diagrams like I did here, you see, pressure diagrams and just calculate the area, that's the total force and it will be very easy. The problem becomes very easy. We'll do a few more problems today and then I'll leave it for next week. So we will do returning wall safety check for next week. All right. Okay. Let's next. So now, until now, what we cover the active. All right. Yeah. So now we'll go to the passive force. Exactly same concept. Just the difference is the failure plane is different. That's why we have slightly different equations. That's it. So passive case. Passive means wall moves towards the what we call towards the swell. All right, itself. I'll show you one example combining both. So we will be all good. Okay, so that's the same thing. Good thing about it, it doesn't produce, in this case, this value. We remember before we had minus 2c that part, but it will be positive. So that means total would be, this is because of the vertical overburden pressure, this is because of cohesion. So both will be summing together in case of passive case. Okay, in the passive. So formula are very basic formula, exactly similar, but look at this. This is what the pressure is all about. The first case is, this is Ka, right? Sorry, Kp. Okay, this is Kp, this is also square root of Kp, right? So formula is simple. Horizontal pressure is equal to vertical pressure times Kp in the passive case, and then you sum the cohesion part using this formula. Same concept. There will be no tensile crack in this case, of course, right? Because the wall is moving towards the backfill. Okay, the formula is similar structure. No need to remember formula. Use properly to draw the pressure diagram, and then it gives us the very easy way of calculating total pressure. Again, this formula, of course, this is just the area of pressure diagram. Yeah, it is easier to calculate area on the pressure diagram than using these equations in a compute. Sometimes we need to get that things. I think that's the table I already, for different movement, you see different types of soils, we use the passive pressure calculations. When there is a C equals 0, not C phi swell, it's a what? Only phi swell, then we can simply ignore this part and only this part we can consider. Okay, so similar structure as we learn in the active case, but let's do one problem, then we will be able to understand. Okay, let's do now. Example 7. Oh, this is, I also took from Dash book. Okay, so look at this. A 3-meter high wall ends in this figure. There is a water table in 1 meter out of 3 meter. Determine the Rankine. Look at this. This is the passive force per unit all. That means this wall moves towards the backfill, not the away from the backfill in this case. All right. So exactly similar structure, similar things. So can we do now? Let's start. Yeah, come on. Let's draw the pressure diagram. Again, look at this. This is C0, right? This is what? Bottom, there is a C value, right? In this case, at the top swell, for 30 degree, can you calculate Kp now? So because P is passive, right? Kp formula is here. Kp equal the other way around, 1 plus sine phi divided by 1 minus sine phi now. For Ka, it was opposite, 1 minus sine phi divided by 1 plus sine phi. Can you calculate that now? So it's a 30-degree angle, the first layer I'm talking about. So 30 is half, right? Sine 30 is half. This is 3, 3 by 2, 1 by 2 is 3. Yeah? Should be 3 value, right? 1 plus sine phi divided by 1 minus sine phi for 30 degree. Can you calculate for 26 degree also? What would be for this layer? Kp equal 1 plus sine 26 divided by 1 plus sine 26. So 1 plus sine 26 equal divided by 1 minus sine 26 equal to 2.56. Is that correct?
Yes.
So this is 3, very easy, that's 2. We already calculated the coefficients now. Let's draw the pressure diagram now. Because there is no C here, that means over there, do you remember the formula we wrote before? Sigma dash B times Kp, but now it's plus here, right? 2C dash square root of Kp. That's the formula, right? For the passive case. Can I show you now? That's what I'm talking about. 7.62, right? That is the formula I'm talking about, right? So in this case, there is no C for the top layer, right? C is 0 for the top layer, so there is nothing there. So it's a 0 point starts. What will be here now? This point. We use the just above the line, Daniel. I think what we discussed before is if there is a 2 layers, different layers, we need to compute just before, above the layer, and just below the layer. So when we use just below the line, then we use the second layer. Just above the line, we use the first layer properties, right? In order to, because there is a 2 different layers. That's good. Yeah. So now how much is the sigma V here? Just calculate sigma V only, right? Can I do that now over there? So it will be, how much it would be sigma V? At the location, sigma V is 0. Over here, sigma V is 2 times what? Vertical pressure is 15.72? 15.72 equal to how? 31.44, yeah? Over there is 31.44 kilonewton per meter square. And then over there at the bottom is, how much is it now? 2 times 15.72, 15.72, very loose, yeah? 15 is very low density, right? Okay. So times, oh, sorry, plus. Another one is what? 1 times 18.86, 18.86 minus 18.86 because of the water table, so we need to minus 9.81, right? That's it. Did I calculate it correctly? 40.49 here, vertical pressure. I'm just computing vertical pressure here in this line, okay, sigma B. Okay, sigma 0, sigma B, different books they write, yeah, different way, don't worry, sigma B, yeah. So that's what we computed, dash, right? So over there is 0, over here is 31.44, this is 49.49. Okay, now use this formula. So sigma B is 0 means first pass is 0, there is no C, 0, so that's why 0 here. How about here, at the end of first layer? So just above now, just above, we don't have C value. So it will be 31.44 times Kp. How much is it? 31.44 times Kp is 3, just above the layer, right? 94.32. Can I draw here? Is it over there? 94.32. So this is the pressure for the first layer. Do you understand? Just above the layer, I mean. But we need to compute here just below the layer also for the second layer, all right, along this line. So now let's check. So based on this concept, vertical pressure is same at this particular line, right? So 31.44 times, can you do now? 31.44 times, what is the below the layer Kp value?
2.65.
2.56. Is it 56 or 65? 2.56.
56.
All right. Okay. So did you get 80.49? So is it 94? Can I use different color for this? All right. Okay. Here you go. So can I do that? So 80 means little bit less. Look at this. For the below layer, this is the one, right? So this value is, can I write here? 80.49, yeah? 49. So this is the only. So for the below layer, that is the case. Above layer, 94. So how about here now? Can I just drop down this up to the second layer? What will be here? Vertical pressure is this much, but we remember we also need to use this. All right. So in this case, what happens? 49.49, is it 49? 49.49 times, what's the K value now? So 2.56 plus 2 times C value. What's the C value for the bottom layer? 10 times square root of Kp. So square root of 2.56 equal 158.69. Oh, did I use Kp also there or no? I need to check. Okay, just wait. First, I'll do this and then. How far is that one now? 158.69. 158.69. Need to make sure now this one, right? Can I check now? 31.44. 31.44 times Kp is 2.56. Oh, I didn't use. I need to use this value also, guys, because there is a just below the layer that is also applicable. So plus 2 times, what is that? C value is what? 10 times square root of Kp. Kp is for the bottom layer 2.56. 2.56. So it goes beyond, not inside, guys. Okay, that's the value from the just from the top layer, but it goes to up to what level? 112. 112.49. So now this is the pressure diagram. Oh, I'll discuss this. Anybody has any questions now? First layer is sand, so there is nothing. So your second part is 0, and just use the first part. But as long as you go just below the layer, it's a clay, right? Cohesion there. So you need to include these cohesion calculation also in the second part. Good? Yeah, determine the Rankine passive force. Yeah, total force only, so it will be easy. All right. So now, can I calculate area of this now? What will be area of this triangle first? It's just the total force, so it should be all good. Easy. Oh, there is a water also. You guys didn't tell me. I need to put the water pressure also, another separate one. Yeah, this would be 0. At the bottom would be what? 1 times 9.81. So can I write this 9.81? This is 9.81 times 1, which is the same thing, right? So there will be 4 parts, right? 3 parts. 1, 2, and 3. I need to sum them together. What is the area of the first one? Come on. 0.5 times 94.32, 94.32 times, what's the height? 2, yeah? Is this, oh, 94.32, the same thing, 94.32. Can I circle? This is the area I'm talking about. So 2, what is the area of this? It's just the trapezium, right? So easy to calculate. 112.49 plus 158.69 equal divided by 2. Average multiplied by height is 1. 135, can I write now? 135.59. What is the area for the water pressure? Total force due to water. So 9.81 times 0.5, yeah? Because height is 1, so it's 4.91. 4.91. So I calculated 3 areas already. That, this is 1, this is for 3, this is for 2, right? Can I sum them together? 1 area is what? 94.32. 2 area is 135.59. 3 area is 4.91. Can you sum them together now?
234.8
plus 135.59 plus 94.32, 94.32, 234.82, yeah? 234.82 kilonewton per meter of the wall, right? Okay, so that's what the total force. You can also calculate, right? You can just calculate where the location also if required, but it doesn't say anything. But you can calculate. I think the solution provided also calculated that. Can I check now what's the total one? What's the total pressure we got? 200, how much we got? 34. But they got around 220. I think somewhere, did we do any mistakes in calculations? It's a 94.32, that is correct, right? 94.32, that's same. And then what's 112.49, 112.49, that's also good, yeah? And then what's the one, 135.65? Oh, this is 135.65, what we did here? Did we make some wrong calculations? Come on, just wait, I wanna check. 135.65 they did, right? Can I check now? Vertical pressure is, can I calculate vertical pressure first? Vertical pressure is 15.72, 15.72 times 2, right? Plus bottom one 18.86, 18.86 equal 34 point. How did I get this 49.49? So this is just gamma is 15.72 times 2 plus 18.86. That's it. I think I used 2 over there also. Come on. So now 49.49. Okay, no, not that. That is not correct. 15.72 times 2 plus 18.86. That's it. 18.86. 18.86 plus 15.72. 15.72 times 2. Oh. How much you got, guys, the vertical pressure at this point, at the bottom of the wall? Doesn't look this is correct. Just the vertical one only, right? The overburden pressure. So now
we need to reduce.
Yeah, reduce water. Yeah, I didn't do. That's the wrong thing, I think. Yeah, that's it. So 15.72 times 2, right? That's the first part. There is no water, so it is good. Plus, second one is just 1, right? I think I did 2. Yes. So equal to just 1 depth, so I can ignore the depth. So 18.86 minus 9.81. Yeah, that's it.
It's 40.49.
I think just when I wrote 49. It should be 40.49, correct. Okay, so now I can multiply that. 40.49, 40.49 times, what's the Kp value for this layer?
2.56.
Plus, and a 2, what is the C value? 2 times C is 10.
10.
The square root of Kp is 2.56, 2.56, yeah. 135.6, oh, that's the thing. I think calculation I did all right, just when I read right, something is 135.65, yeah.
65.
Now you can calculate, this area will be different, guys, now, come on. So plus, can I do that now? I will check, right, 112.49 plus the 135.65, right, 65, yeah, equal divided by 2, and it's 124. This is just 124.07. Yeah, area of the second phase. So this will not be that 124.07, right? Plus 94.32 plus 4.91. It should make now 223.3. 223.3. That's the vertical pressure. I wrote wrong there, right, guys? Yeah, that's the kilonewton per meter. So we calculated, look at this. Just looking at the pressure diagram, we can calculate total force. Look at this book. Calculated every pressure everywhere, and they drew the diagram, of course, but they show the calculation. I think that is what the pressure, total pressure is. Good. Total force acting on the wall is that. Do you understand now? Yeah, similar structure, similar formula, just the passive coefficient and the active coefficients are different. That's it. Okay, so you can compute that. How about now combine both active and the passive? Okay, so we did the passive separately, we did active, so now both together. Okay, active and the passive plus together. Here you go. Look at the problem. Is the problem, example problem, active and a passive both? This is the I took from another book because this looks very good, right? So now what happens is, look at this. There are two layers. Can you tell me how this wall is about to what? Swing. Over there it may go that side, right? Yeah, this side is active side. Okay. Over there, because you see look at the wall movement. Wall movement will be like this, right? If there is a pressure from there and that side, isn't it? In this case, it moves away. That side is pressure, right? From when this side, it away from the backfill. When you compute there, it's a passive side. Yeah, this side is active side. So now you need to draw pressure diagram for all of them. Oh my God, it takes time. Can we just do calculations and just put over here, right? Can I just remove this first so that it will be clear to draw the pressure diagram? Let's draw only the passive first. Passive is 4 meter, 20 kilonewton, 30 degree. What is Kp? Kp for 30 degree is how much? 3, right? Yeah? This is the same swell both sides. Sorry guys, yeah, I didn't give that value. So same swell here. And that's the value. And over there, what is Kp for this layer? Ka. What will be 25 degree Ka? So Kp there, Ka would be here what? 1/3, right? Yeah. So the Ka at the top layer is how much is it? 25 degree, 1 minus sine phi, right? 1 minus sine phi divided by 1 plus sine phi for Ka. 1 minus sine 25 close equal to divided by bracket 1 plus sine 25. Did you get 0.06406?
Yes.
406, right? Can you calculate Ka for the bottom also here? Because I'm using this K, oh, yeah, already there. Anyway, it's good. 30 degree, that's done. What else we need? Nothing, right? There is no C value, so we can ignore the second part. Okay, let's calculate the pressure here. What will be the pressure, vertical pressure at this point? Is what, 20? Do you understand this? Because this is there is a surcharge 20. So pressure at this point is 20. What will be vertical pressure at this point? Just calculate the vertical pressure only. 20 plus 19 times what? 2. 58, right? At this, I'm just calculating the vertical pressure only so that it will be easier for me to calculate horizontal pressure later. What will be here? Vertical pressure at this point. So 2 times, oh, that's a 20 plus 20 plus, that's a 2 times 19, 2 times 19 plus, and 4 times what? 4 times, there is a water table, guys, yeah? So you need to do, don't forget that. So what is the 20 minus? 20 minus 9.81, right? Okay, so it's a close equal to, did you get 98.76 here? Yeah, So I got the vertical pressure at 3 locations. Now, always don't forget this water. Can I draw water first? Because I forget that sometimes. This is the water pressure, right? Yeah. You see? And there is a water pressure from this side also. And it is equal and opposite. What happens? This pressure from that side, water, this pressure from that side, what? They cancel each other, right? They're balanced, right? In the wall, both sides have the same water level from both. The pressure is same, they're computing, right? We may ignore this. I think this textbook has used that, but later on, we don't need that. If pressure is from both sides in the same level, that means it is hydrostatic completely. Can I draw now? What will be here? What will be here? So the QS is always, we need to multiply by KA, right? Yeah, so what will be here now? Pressure at this point. This is QS, there is a QS at the top, right? Yeah, so now can I do this now? Q, how much is it? So QS time KA, QS time KA, how much is it? 20 times 0.406, right? So that's what it is at the top. This is just because of the surcharge. Okay, if there is no surcharge, it would be 0, right? What is that now? Can you compute this? How much is it?
8.1.
40 times 0.406 is 8.12, yeah? So 8.12 here. So what will be here now at this particular point? Active pressure, I'm calculating all active. It's a 58 is the vertical, right? Overburden now. There was no over, so that's a 58 times, what is Ka value for that? 0.406, 23.55, is it? 23.55. Just above the layer now. Daniel, yeah, I'm using the first layer because there are different properties, so I need to calculate just below the layer also. Exactly same. How much it will be just below the layer? 58 times Ka is what? 1 divided by 3 below the layer, right? That's it. So it would be 19 point. So it will be little bit less, yeah? Interesting. Come on, I'll use different color. Because Ka value is smaller. Okay, good. That makes sense. So this will be color, come on. Give me the better color so that I can, just below the layer, I'm calculating that, just below, all right? Okay, look at here, my writing. This would be 19 point, how much? 19.33. This point, right? What will be here now? At the bottom. What is the vertical effective stress? 98.76. Right? And then what's times Ka is 1/3. So pressure giving is 32.92. Can anybody explain me what might be the reason horizontal pressure just below the layer over here is less than the above the layer? What is the reason? Because of different type of swells, so that coefficients are different. Done now. It's all calculated here. How about passive now? This side. Can I calculate passive also? So because there is a water I already drew outside, only the passive. What is the passive coefficient here? 3, right? So what will be here now? Can you draw now passive? Maybe different layer is better and different color would be better now. Okay, this is for passive. Is it 0 here? It will not be, yeah? It will be 0 or it will not be 0. Can you answer why I had this here, but I don't want to use this now here? Can you explain why? That was because of what? There is a over the what surcharge pressure at that point. That's why there was a pressure here. But for this case, there is no surcharge over there. So it should start from 0. Do you understand? So what will be the value now here? So this value 98 point, oh no, not 98, this value. So how much is it the vertical pressure at this point? Can you calculate vertical pressure only? So what, 4 times 20 minus 9.81, yeah? This is also swell, right? The same swell this side, either equal to, how much is the vertical pressure at that point for the passive case?
20.76.
20.91 equal, just wait, 20.91 minus 9, oh no, it's just 20. 20 minus 9.81 equal times 4. 40.76, right? So this is 40.76. Now you need to multiply by Kp. What is Kp? 3, yeah? Look at this, passive force is so big. This is 122.28, right? So now, can I draw the force now? I drew this all. Now, I want the force. That means calculate the area. That's it, area of this diagram. What will be area of this now? So height is what, 4 meter? So 40.79, oh no, 122, 112.28, 112.28 times vertical is 4 multiplied by 0.5. Did you get this value? 224.56? 224.56. This is the passive pressure, force from this side. How about this now? What is the area of this shape? So 19.33, 19.33 plus 32.92, right? 32.92 equal divided by 2. This is the average times 4. So 104.5. Yeah. So what is the shape of the first one? So 8.12 plus 23.55, 23.55 equal divided by 2 multiply by top layer is 2 meter thick. 31.67, did you get this? 31.67. I'll check with the answer if some computation later on that's wrong, that's okay. So what? Earth pressure distribution with the depth, that's all right. Passive with depth is all right. How much is the total now? Can I just calculate total? It doesn't say anything, just the pressure distribution, so that should be fine. Okay, but we may calculate the total active and the total passive. Total active would be 31, or maybe we need to calculate location also. Yeah, location also all right, because we already know we can divide this into, you see, different shapes, right? 1, 2, 3, 4, where we know the centroid, and that's a 5. That's it. Okay, so we can calculate those all. Can I quickly check whether the total active is what? Total active equal, how much is it? 31.67, 31.67 plus 104.1550. 104.50. Total active force is, how much is it? 31.67 plus 104.5. 104.5 equal to 136.17. Okay, so kilonewton per meter of the wall. So this would be, that's kilonewton per meter of the wall passive force. That's it. Okay. So now you can calculate the centroid. We did that a lot, right? You take the moment at the base of the wall. So this is forcing that way. Other pressure are coming from that side. So now you need to minus this passive force. That times that, and you need to use the area. Can I check now? Look at here, what they do. Oh, they plotted differently. I think 8.2, that's good. For each case, surcharge, they plotted different. So this is 8.2, that's what it is, right? And then there is a 15.6, right, at the bottom because of the other one. Can you add them together? 15 plus 8, how much it would be? 15, 8. So they did the diagram together. So I think that should be equal to this, 23.55. Yeah, sum of those together. I did at one time, so it will be easier for us. You see, I did one time because I calculate the vertical pressure because of the all, so it will be easier for me to multiply, right? This is 23.55, that's all right. At the bottom, how much was? 32.92. Can I calculate that? Is this, if you sum them together, is that what it would be? Sum them together and that, it should be 32. Can you do that now, please? 6.7. 6.7 plus 12.7 plus 13.6 is 33. Yeah, of course. This is 33. What I calculated before, this is 32.92, which is just very close to 33 anyway, right? Yeah. So that's the thing they did. That's all good. These calculations are all correct. This is water. So 39.2. This is water. 39.2. I would ignore this. Yeah. Because what? That will be the same from the both sides, isn't it? The pressure. And this is, did I calculate 122.4 for the passive? This is 122 point. Oh, 122.4. What did I do here? Maybe I wrote the wrong. Is it 122 is the force, right? So how much is this? 4 meter of wall, so 20 meter of the clay. Anything other given here? Can you check again one more time? 20 minus 9.81 equal times 4 equal to 40 point that. That's the vertical pressure, right? Vertical pressure is just that. So that would be 4 times 20 minus 9.81. That's the vertical times 3. Yeah, 122.28. Just writing. Yeah, 120. So it will be slightly different, guys, now. How I got this, okay? I wrote, my calculator has something, I do something else. So that's what is wrong. So 4 times, what's the gamma? Is 20, right? 20 minus 9.81, right? And then Kp, which is 3. Can you compute that? I got 122.28. Make sense? So this 122. So area would be now times 4 times 0.5. 244.56. This is 244.56 kilonewton per. That's it. So again, the concept is exactly the same. What they did in the example here is they use separate type, like a surcharge differently, layer 1 differently, they did. But I just try to combine all. As long as you calculate the vertical pressure at different points, and then you use the coefficient, lateral pressure coefficient, that would be enough to calculate. Any questions for me? Solution is here, you can check, right? These are the diagram, and they calculated all, look at this. This is the active, I think. The first they calculate active. Total active, how much is it? This is the total one. This is the active one. This is active, right? Because of the surcharge, that much, they didn't sum them together, yeah? Did they? So that's, if you sum them together, it should match with ours. Can I compute that? Can you add them together? 8.2. That's the active pressure, right? Yeah. And then they must be done. The next is force, right? These are the force and the moment. You see force. Can I check now force? This is total is 78.4. Total active lateral force without water is that, is it? No, that's a water. Everything is 215.2. Can I check now? How much would be our case? So total I calculated is this plus, what's the water one? So that's the water one. What is the area of the water? Can I do that now? 4 times. I just ignore the water, but they calculated both sides and they minus. Not sure why. So now 4 times 9.81. 39.24, right? This water, 39.24. If you calculate the area of this, times 0.5 times 4 is 78.48. 78.48, right? If you sum them together, 78.48, how much it will be the total active pressure? 136.17 plus 78.48. So total is 215 kilonewton. 215 kilonewton per meter. That's total active kilonewton per hour. Is that what they got active total? Oh, that's not the force. You see 215, yeah, it matches with ours. Anyway, okay, that's all good. Again, okay, so there is an active and a passive. So always if your wall is supposed to move away, this is the passive, and the away is active, and the towards the backfill is passive. So you need to compute both active and the passive and then balance together. If you practice this is very simple as I described. It's just a little bit different types of soil. We need to compute, there is a surcharge, we need to compute and so on. Okay, so if you check, our answer matches with that. How about the passive? Passive, how much we got? Passive force is 244.56, but there is a water also. How much we calculate? 78.48, right? 78.48. If you sum them together, how much it would be? 244.56 plus 78.48. How much is the total passive? 244.56 plus 78.48. 78.48. 323. Let's say 323 kilonewton per meter. Is that what they calculated at the end? Yeah, 323 is the total passive. That matches with ours, right? I think the way I do is a lot more clear than what they have done in separately. So it's better. Again, the rule is just draw the pressure diagram overall and calculate the area for the force. Yeah, divide the area into the shape, different 2D shapes, and then you can calculate moment at a point to calculate the resultant force. What's the location? That's it. So they calculated what's the last. This is what? This is the moment. So this is the resultant force is 2.09. That's it. Okay. So lateral force is always what? PP minus PA, which is PP is more than PA. So that's the total lateral force. Ratio of the moment we calculate passive moment divided by active moment. It is just like a little bit of extra calculations, right? Do you understand now what we learned until now, guys? Okay, what we learned is we learned Rankine, active and a passive pressure. We know how to calculate, draw the pressure diagram, and then calculate the area of those diagrams. Then it gives the total force. And we can calculate, taking the moment, we can calculate the location of the force. That's it. Sometimes we can calculate the resisting moment, like a passive moment divided by active moment. Can you check this problem one more time at home? Yeah, do it by yourself and check the answers here. So it makes sense because my answer also matches with them anyway. All right, move on. What time? Oh, time goes like a quick one. So now another case. This is the same thing, guys. Look at this. What is phi is equal to 0 swell? What that happens now? If phi equals 0, I want to ask question now. Who is good at answering? Maybe. If phi is 0, what is Ka and the Kp? Who want to answer quick?
1.
1. You see? So that means nothing. There will not be any issue with that, right? If it is only clay, then we can directly use this equation. You remember the depth of tensile crack in the clay? The equation was ZC divided by what? 2C divided by, I think, gamma root Ka, right? Or Kp, whatever. You see, this is 1. That means that's what? You see, simplified version of the crack when the phi is 0, isn't it? So same equation you can use even for these different cases, right? Yeah, you are all right now? So this is just showing you the calculations. This is the same thing. We can calculate the pressures and then it acts as the what? 1/3 of the height, of course. That's what we know. As long as this is vertical, back face, that's all good. And also the horizontal backfill, there is no, like a not sloping like this. Okay, this is simple. Let's move on now. Okay, that's what it's calculated here. You can check. Now, different case. Still Rankine, C equals 0, only phi swell, right? C equals 0 swell, quasi swell, like sand. Vertical back face is still the back of the wall is vertical. Look at this. There is a sloping backfill. Backfill is sloped now. We are not retaining the horizontal backfill, but sloping with the angle beta. You see, the backfill slope is angle beta. So in this case, the same concept. You use these equations to calculate active pressure. You use these equations to calculate the passive pressure. You see the beta angle of the slope of the backfill. And then you just draw the pressure diagram. In this case, look at this, because wall is vertical, the pressure acts parallel to the backfill. You see, this is the direction of the active pressure. You see, so now, of course, then you can calculate the area like this pressure diagram, right? You see now, this is the active pressure diagram. Same thing, just there is a beta extra. So that means you need to use these equations to calculate Ka and Kp. If, look at this, you can use this equation for the general case. If beta equals 0, what happens? This is 1 minus sine phi divided by 1 plus sine phi. What is this? This is the not sloping if beta is 0. Same thing happens here. It will be 1 plus sine phi divided by 1 minus sine phi. We just used before, right? This is when beta equals 0. You don't need to derive formula, but use the correct formula. If there is a sloping backfill, you use this equation to calculate the lateral of pressure coefficients. Did I make clear? It is easy, right? Okay, so let's move on. Next. Of course, there is a derivation, how that formula is derived. I have taken this from the very good book. Bohl's book is very good, one of the very good. Even though it's old, this is very good one, right? It's on how to derive equations and things. Forget about derivation. Just use the correct formula. We'll be all right. So now, sloping backfill, vertical back face. Yeah, that's the derivation discussed now. All right, look at this. Sometimes they even to calculate that for different value of beta and the phi, they use the Ka value in a table. They give you in a table value, Kp value also. You can easily calculate using the equation anyway. All right, the equation means this equation. I mentioned this for Ka, this is for Kp. If you use different value of phi and the beta, you get different values. These all table values are all right. We don't need this nowadays because before we didn't have good computers to calculate things. That's why we developed tables to give you. But now we don't need that. We can just plug in your calculator and get the formulas. Okay, so there is a very simple tutorial. I'm not going to do that. Simple tutorial based on what? There is a sloping backfill. That's it, right? Still the wall is vertical. Yeah, and then as I said, always the pressure distribution is like this. Yeah, use the same equation, just you need to do the Ka calculation. Ka, active pressure equal, there is a formula, right? Very long formula now. We don't just use 1 minus sine phi divided by 1 plus sine phi. All right, just use the Rankine equations here. Make sense? You can check this. This is very simple formula. Now, another case. You see now, if I swell, vertical back face is still the back of the wall is vertical, but there is a sloping backfill. But in the case of C5 swell, before formula was C equal 0, only phi formula. You understand what that Kp and the Ka I discussed before? That's only when C was 0. One guy, I don't know, these guys take very long time to derive this relationship. They derive the equations for Ka and the Kp for C phi swell condition. For example, if you put C equals 0 in this equation, you will get back to these equations. All right, they try to extend the formula and get those values. This is for C phi swell, and then this is for active case. There should be a passive also. Is there? C phi swell. Yeah, this is the passive one. C phi swell, passive case. The same guys, they give us the formula. This is very big formula, all right, to calculate lateral earth pressure coefficient. That's why they sometimes give the values here in the table. You can quickly check based on the phi and alpha degree. You know what alpha is. Now, this book use alpha. I use beta for the slope. So don't confuse with the symbol. Make sure you understand what symbol relates to what in different types of books. So we have this also. You see now? So we have the formula for what I said, C phi swell, still the wall is vertical, and then there is a sloping backfill. Next, what is next? There is a sloping back of the wall, and then sloping backfill. Oh my God, that becomes very complicated now. You see, slowly, we are going to the complicated problems. Next. So this is what? This is C equals just phi only swell. Yeah, and there's a sloping back face. Back of the wall is sloped. Yeah, and the sloping backfill also sloped. This will be very complicated for the Rankine theory, right? So now this is what we calculate as the active Rankine coefficient using this relationship, right? These two, 1991, they developed the formula for this. So this is also, there are different formula for this, and then where is the phi? You see now, W active, W passive, theta active angle, theta passive, xi active, xi passive. Look at the formulas. These guys are very good giving formula. And this is the final formula when everything is equal. So we get the similar formula we did before. You remember this formula? We did in the before. So what we are doing now is adding one more case and making the formula for each of those. Okay, so if you are good at calculating anyway, you have a calculator, so you can plug in the numbers, you get the values, coefficient, and then draw the pressure diagram and then calculate. Maybe, yeah, getting complex and complex. I think it went little bit above your undergraduate level now. In undergraduate, vertical wall, frictionless wall, just the horizontal pressure, little bit of surcharge. I think that's it, right? But now we are getting little bit more cases for that. Concept is exactly same. There is no difference in concept. Only thing is we need to plug in those numbers in different equations to get the value. So now what we did until now, even though whatever the back face of the wall is, what is the surcharge, like a sloping backfill or the horizontal, always assume what? There is no friction wall and the swell. Friction value, we use delta in palm, right? Delta equals 0 until now. That's why we are still using Rankine's theory. But if there is a friction between wall and the swell, now we need to move on to Coulomb's theory. You understand the difference between these two big theories, right? Rankine's theory is used only when there is no friction between wall and swell. But if there is a friction between wall and a swell, we need to use Coulomb's theory. Are you ready to move on to next? What time? Oh my God, so quick time goes, right? You guys have another class, so I'll not take long time today, right? I'll leave you. Yeah, so just introducing the Coulomb's theory now, and then I'll leave you, all right? So could you please, guys, look at these tutorial problems and also practice the tutorial problem. Can I just do this? I say, can you practice the tutorial problem at least these extra tutorial questions, all of them? Because these are all related with the Rankine's theory, right? All 5.4, 5.5, 5.6. We did many and we have solved already, right? Just few, try again. But this stability of wall, and then this is another stability of wall. This is the complex one. Look at this, everything we have. This is the what? There is a friction angle. That's why we need to use Coulomb's theory. Then there is a what? Surcharge in the slope, and there is a sloping. There's many things here, right? At least these guys, they give the vertical wall, so it will be a little easier, okay, compared with sloping back face, right? So I'll cover 5.1, 5.2, 5.3 next week. Next week means week 6, all right? All others for this, could you please do it? Okay, that makes a little bit easier for me. Okay, I'll just introduce only, I'll not go in detail. Now, move on to the Coulomb's theory. Do you understand when the Coulomb's theory are used? Only look at this. All cases of swell, mostly we use the phi swell, not C phi swell, but there is a sloping back face, sloping backfill. There is one extra thing. There is a friction between wall and swell. So that's what it is written here. You see? So frictional resistance contributed among ruptures, failure wedge is that, and there is a wall friction. That's what I mean. There is a wall friction, and then there is a plane strain problem we consider. And then if you want to know how to derive equation, just go through geometry. This guy has done a lot, all right? And then derive the equation again. At the end, what we get? Active lateral pressure coefficient. So we can use directly this formula. How easy that is. Yeah? So for active, there is another formula for passive. You see passive pressure here. That's the active pressure coefficient. That's the passive pressure coefficient, considering delta. When there is no friction, if you put delta equals 0, you will get the similar equation before. You see how quickly that turns around. They are the same. So because the wall is sloping now, there you go. Wall is sloping. So how the pressure X is, let's say this is the beta angle with the backfill angle. What happens now is when the pressure, it acts in a, look at this. This is the perpendicular to this face. And I draw this now, perpendicular line to the back face. And then it acts as an angle of, you see, the angle of delta, friction angle. So that means it can be that side, it can be this side, depending upon the sign language that's written there, right? And then because this is also sloping, so there will be, we can calculate horizontal component using this passive as well as cos delta minus eta. But for active, we use delta plus eta. Eta is the angle of the backfill here. This is the angle, you see? That's the angle we call it eta angle, right over there, because this is the sloping back face. Okay. Maybe I'll stop here today. Okay, so we will solve one problem using Coulomb's theory. I think that's here, and then it will be easier for you guys to understand. It's all right. In summary, what we covered today. Okay, we started learning about lateral earth pressure theory. That is nothing but if we calculate vertical pressure, we multiply with a coefficient, like you see lateral coefficient, then we get the horizontal pressure. Once you draw the pressure diagram, then area of the pressure gives the total force. Location of the pressure is just taking the moment about the bottom of the wall and then equating with the force. So M divided by F is giving you the what is the resultant location, right? And then we had covered many cases like there is a water table, what we do, different layers of soil, how we draw the pressure diagrams, and then we have learned few formula for if there is a sloping backfill, what we do, yeah, and then also for C5 soil, what is for phi soil, only for C soil. So different type of soil, different type of coefficient calculation formula we use. Now this Coulomb's theory is the main one when there is a friction between wall and the soil is assumed, which is in fact that is correct. But in reality, many people, they don't want to compute this complicated equation, so there's basic use the particle is the basic what Rankine's theory in many cases. But Coulomb's theory is more scientifically accurate in order to calculate those type of things. Okay, so we will do one problem, start problem next time, week 6, using this. Okay, the formula, how we use that and how we compute the pressures. Once we do the tutorial, it will be more clear and easier. Okay, I'll leave it here in slide number 59 today, yeah, and then I'll continue from there. Before I stop, any questions, guys, from anyone? Come on.
Yes, sir. I have a question.
Yeah, come on. Yeah.
So it's about tutorial from week 1.
Week 1. Okay. Can
Yes.
I go there? Thank you for that. So this is discard that and tutorial from week 1.
1.10.
Can I just open up this all of the tutorials and then 1.10? That one?
Yes, I just don't clear about calculating Q ultimate.
Sorry, say again.
Can I just, sir, can you hear me?
Yeah, I can.
I just want to know about Q ultimate for clay layer.
Q ultimate for the allowable bearing capacities for the clay layer, right? Oh, I think there are formulas and calculations. Didn't I do this in the class?
We do.
Okay, can I go there then so that it is easier for me to explain? Yeah, instead of redoing everything. Come on, go down. Let's wait. Oh, no, not the settlement. I think it's still the ultimate bearing capacity, isn't it? Yeah, that's the one, isn't it? Yeah, this one. Yeah, what happened?
Yes, I just want to know why at Q ultimate why all sum up together.
So now Q ultimate.
Yes. Like 1 plus 0.2, 0.3. Yeah, at Q ultimate. No, the previous one, sir. Yes. Like for clay layer.
For the clay layer, right? You are talking about that's the Hansen method we are doing, right? This
Yes.
is for the sand layer. That's very clear,
Yes.
right? You calculate
Yes.
that, right? For the clay layer, that's what the equations we use. What is your question?
Yes. What my question is why you are sum up together 1 plus 0.2 plus 0.3, 0.2.
This one?
Yes. I just don't clear that.
Oh no! I think because point plus. Oh, okay. Just if I calculate, then I may get. But this is the solutions they provide, right? So what is this is for clay layer, right? What's the equation? NC, right? So
Yes.
1 plus point. Can I check? Okay, come on. It's for the clay layer. Which one? Sand overlaying clay. This is the condition, right? Our condition. Yeah. This is the 3 cases, right? So then what's the ultimate capacity? Oh, I think we did that ourselves, but I'm not sure. Did we do this summing together or not? Did you check our recording? I don't think that we did. Why they sum it together?
Yes.
Here.
Yes.
That was your question, right?
Yes.
I think we can compute the ultimate for the clay layer. So you may not, what is the Q ultimate in the formula? Can you do that now? But this is the one, right? Yeah, that's the one you are calculating, right? Yeah, so
Yes.
what is the formula? So this is the one. So bearing capacity of the lower compound Q ultimate, but also using B equal footing dimensions. That's the one, C5 lower swell. I think they are. Come on. Oh, I didn't check that particular their solution. I think we did that ourselves, and I think answer was matching. Is it? So we will. I'll check this. Right? Can I explain you on Wednesday? Right? Yeah.
Yes, sir.
Yeah. In our modeling class, because I didn't really check their solution. I tried to solve by myself, and the answer was matching, and that's. I will see why they sum together and find out. Okay. It's good.
Yes,
Yeah.
sir. Yes.
Any other?
And yes, another one.
Yeah.
Yes, it's at 1.8.
1.8. Oh, that's I'll check that now. And discard 1.8. Oh, not that one. Come on. Where is this? Yeah, that one. 1.8. Yeah. What happened? You didn't get answers?
Yes, I do get answer, but I just don't clearly understand about applied pressure. That's at the solution.
Oh, in the solutions. Okay. Yeah, okay. So now foundation carries this kilonewton of load. That's okay. So that's a 19. That's a C. That's a 5. Foundation depth is given. Factor of safety is given, right? Yeah. Oh, determine the factor of safety we need to find, isn't it? You need to calculate ultimate first using two methods or one method. So Meroff and a basic, 2 methods, right? Calculate using these 2 methods the ultimate, and then given load is what? That one is the foundation safe for the, oh, this is already safe if you get a very good factor of safety, right? Yeah, that's why yes, okay. And I go to the tutorial solution, so it will be a little bit easier. Do I have, or did I upload?
Yes, we do have solution.
Yeah, I think I provided that. So that's a 4, oh no, not 4, 3. Okay, thank you for that. Yeah, so we need to look back and see there is a solution, that one. Okay. Okay, so now, so the 1.8. This one, right? Yeah. So that's the same. This is for Meroff, right? I use this equation. I think that's the general capacity equations. So what you're not understanding one completely?
It's applied pressure.
Yeah, that's a given load. Given load. Oh, okay, good.
Yes, I mean, is that true? Like for one, I just don't understand about two multiplied by 1.
Is it the square footing? Continuous footing.
No,
Yeah.
it's continuous.
Continuous footing. Okay, I can explain this very well for you. All right. Okay, it is not square footing. Can I do now? Come on. Where is my PowerPoint? Okay, this is strip footing. Okay, so there is a difference, right? Thank you for this. I can. Here you go. My problem is if I do something by myself, I can explain well. If somebody's, I need to do by myself. If I get the correct answer, I don't look at what they do really, okay? So look at here. So this is, can I draw the 3D diagram, right? Okay, 3D diagram, right? Look at this. If it was square footing, right? Let's say square footing first. You see? It is like this, right? Footing is square footing, right? So if there is a load given onto this, so that means area would be L times B, isn't it? Okay, so that means given load P, the pressure given from this, right? Pressure from the external load would be, let's say, pressure equal what? P total load divided by area, isn't it? Right? So that means what? P divided by L times B. Do you understand if it was square? If it is strip footing, what that mean? Can I draw now? There you go. So now this side, it keeps going. That side, right? So this is continuous, right? Strip footing means. This side we know is a 2 meter, right? But because we cannot go continuous, how long you calculate the area? So we just took 1 unit length of area. So we calculated for this part only. So area equal 2 times 1. Did I make clear now? Fine?
Yes, sir. Yes.
Yeah, okay. So that's the reason we took only the unit length of the wall. We didn't go continuously strip footing everything, right? Of course, even the given load is per meter. For example, I think the given load was what? 350 kilonewton per meter, right? So they also didn't give the total load. They just give the per meter. So that's why I use the per meter to calculate the pressure given by the external load. Make sense? Good.
Yes, sir.
Any other? Okay.
No, sir. Could you please upload solution for 3.4 for week 3?
I just left one question and you guys asking for the solution. You see, this is little, I know.
No, because I just want to compare with my answer. So.
Okay, intentionally I did that because at least one question you gotta try. Okay, so that's what it is. But anyway, so I'll check your answers, right? Okay, next. When
actually, so some of the parameters were unclear in the 3.4.
Is it unclear? Good. Okay, come on, let's go to there now. 3.4, right? Oh, okay, so 3.4. Solution would be fine, yeah? Good. I'll do it. What happens now here? What is it? Can I just explain, right? Yeah. So this is the load is applied on the 15-meter long pile, and this is the diameter of the pile. Everything is all good, right? Only we need is what? Frictional variation. Look at this now. Can I just explain this if I can? Over here, look at this. What happens is, because this F is given already 40 here, right? Because this layer is different than that. So this is different. So we need to have two different calculations, right? So now you calculate ultimate bearing capacity for only the frictional resistance, only this part. And then you calculate ultimate that part. So then sum them together total. That's okay. Draw the variation of pile load. So how much will be load variation now? How much? How you calculate that? Because we know already the friction load, right? Now, how it varies with this? You guys are quite okay. Okay, I'll upload the solutions, right? Okay, and then you can see that. All right.
So, but what type of soil do we consider on this?
Oh, no, this is a frictional. Oh, soil type, is it? This is not given here. Where is the apply along this? Do we need, because already F is given? Why we need soil type if F is given? Friction is given, right? Yeah. So how you calculate ultimate load for friction? Because this is friction, it should be clay. Okay. Oh, it can be sand. I don't know. But because friction is given, can I calculate now? What is the shaft friction, shaft load? QS equal, what happens now? Let's do only first layer. What happens the first layer? QS. What is QS means? Sum of what? Perimeter area, right? Area around the pile times what? Friction, isn't it? Yeah. Is that anything else I missed? No. Because if this is the perimeter of the pile, that's the friction, right? Friction is different, so we need to draw different friction. So you calculate QS for the second layer also. This is one layer, QS is the second layer. Yeah? And then you sum them together and you can back calculate for the pressure distribution of the pressure pile load variations with depth, because there will be a different change. Oh, you guys very quiet now. Come on. So can I?
During the calculation of QS, do we consider the length as well?
Yeah, of course, length. Of course, perimeter comes, weighted perimeter comes with the length.
Okay.
This is perimeter, of course. Perimeter is where the friction is all about, right? Around, right? So that means what? I think pi, what is the circumference of is this the circular? Diameter, yeah? It's a circular pile, isn't it? Yeah? So pi d is the what? Around, right? Around, and then multiply by length is the p. You see this one? So p. So at the top is what? That's the same thing. And then how? Because this is the point load, right? 1500 comes at the top. You see 1500 here, right? How about here now? How much is taken away by this friction? Can you calculate now? Can you do this calculation? Could you please? Pi times d times L times F. Can you do that now for me? Come on. I'll solve you now, right? Okay. Kind is good. Okay, let's solve it. So pi, right? Come on. So that's a pi value times what? Pi times d is what? 0.5? Always use the correct unit, right? Millimeter is given. Okay, don't mess it up that. Times length of pile is 10. I'm talking about the first layer only. All right? Yeah. So 10. So pi d times L I did. So what is the frictional resistance in the first one? So now what is that? what? 40, yeah? 40. 6 to 8 is taken by the first friction. Oh, come on. Can I write anything I miss? I think friction is just this formula. I need to check the formula, right? If I miss, then I'll see that. 6 to 8, right? 6 to 8 kilonewton is taken by this friction. So at the beginning was 1500. So what will be here now then? 1500 minus that. How much is it? 1500 is minus 6 to 8, right? 6 to 8. 872, right? At this point is 872, right? And then you can calculate the friction from the second pile also. Can you do that now? Sum of perimeter times F. How much is it? Sum of perimeter is what? Can I write now? Pi d times 5, right? And then F is 70. Can I do now? So how much is taken away by that? So pi d is what? Pi times d is 0.5 times 5, right? Length of that layer. That is the 1 times 70. So second layer will take about 550. I'm just writing approximately, all right? Okay, 550 from the second. So now it was 800 that. So now how much it would be in the over here? So 800 what? 872, right? 872 minus, that's the second friction is taken away. That load is down now. So what is that? 550, yeah? 550, how much? 322? So over here it will be 322. Can I draw now? Pressure distribution. Over here is 1500, whole load, right? That's the pile it is taking. I'm talking about this external load. 1500, and then it will be what? That point would be 872, and then bottom would be still there, little bit, not taken by all fully. So this is the 322, right? So if pile is like this, the remaining, the load, it should taken by the tip of the pile. Otherwise, it will not be stable. You understand what I mean? This is the pressure distribution. Did our answer match with that? 1500, 871.6, makes sense? Yeah, that's okay. You see? That's what I already calculated. Fine, is all right? Yeah, now I explain how the pressure is distributed, because at the top, whole pressure is there, right? But because friction will take some of the load in the first layer, and there will be another pressure there. So that's what the variation of load. Good. And you do the other way around, exactly opposite now. You see? So because load is given, right? This is load distribution is given. First layer is like this. At the beginning is 1500, 800, and at the bottom is 300. How much you calculate friction now? Just exactly do the other way now for the second part. This one. Z is given, variation with depth is given, you calculate the friction back way. So exactly opposite way.
Okay, sir.
Is it good? Good. You don't need solution now, yeah? But if I have, I'll upload, all right? I'll check and then I'll upload that. No worries. Any other? Yeah, it is all right, Achay, yeah? Is it good?
Yeah, I had one last question actually.
Yeah. What's that?
Yeah, that's in general, like that's in concern with shallow foundation.
Yeah.
So what I observed is, like during we were solving tutorials and lectures. So
yeah,
during the calculation of loads, we didn't deduct the weight of concrete, I guess.
Oh, yeah, that is, yeah. For now, the weight of concrete is, we just equated with the what, gamma of soil, right? If there is different given, we need to use that. Thank you for that. Okay, can I explain this problem now? Okay, why we don't do many things? Okay, I'll tell you, right? Look at here, how we do. If this is a foundation, thank you for this question, all right? It's very good to understand the basic principle, all right? So now, the main thing what we do is, this is the given load, yeah? Q, external load given to it. So it may include this concrete load also, self weight of concrete. or any wall, brick or whatever, okay, self-weight we can include. And then what we did is we calculated the pressure from the bottom, right? Ultimate bearing pressure. Do you understand the swell given to this? What is the ultimate bearing capacity of the swell, this one, right? We calculate Q ultimate. Q ultimate. Look at my writing. Q ultimate. All right. What we did is we tried to calculate now. We tried to calculate Q allowable. Only Q allowable we allow from here. All right. We don't allow the ultimate there. What we use the factor of safety, right? Yeah. So now Q ultimate divided by what? Factor of safety, isn't it? Factor of safety we use like a 3, 4. So that means this self-weight of the concrete can be included within that factor of safety, right? So we don't go in that detail. That is the one reason, yeah? Another reason is if you want to be accurate, please go ahead. You can calculate that, all right? We didn't consider that part here. Because you see, factor of safety, we are using 3, 4 in geomechanics, right? For example, if we calculate ultimate bearing capacity, 300 kilopascal, we are just allowing 100 kilonewton of the load. Forget about this concrete, okay? It will be, that is the reason why we have very big factor of safety in soil engineering, because we don't go detailed calculation. Really, we don't know how the swell varies from a small part here, just close to it is different. Okay, so we try to accommodate overall. That is the reason we didn't use self-weight of concrete here. But you can, if you want to be accurate. That is nothing, but you need to add to this. Okay, when you use the calculus of the concrete, you need to add to the given load. Q plus weight of the concrete gives the up pressure from there, right? Yeah, that's the given pressure from there. And that's the supporting swell. So we cover only this part. So we didn't go to the given load part that much anyway. We try to balance given load and then pressure given from the swell so that we are safe by 3 and 4 times. You see, that is too big anyway. Okay, good. Yeah, that's the way, Achay. That's a good understanding. Thank you for that.
Nice. Thank you.
Any other question? It's good. Thank you guys for making interactive. I'll check that how they use that solution. I'm sure we did that calculation and we got the similar answer. So I didn't check how they put that over there, but I'll have a look, and if there is a reason, I can explain you on Wednesday. Good. Yeah.
Yes, sir.
Okay, thank you guys. Best of luck, right? So almost everything is done for your assignment you have been doing. Assignment 2 I will upload this week. Okay, which is similar to what we will be doing on Wednesday. Okay, in the computer modeling. All right. So please come to the computer modeling. We will look at your assignment and we will do one problem similar to that. So you know how to do your assignment. All right. Don't miss Wednesday numerical modeling workshop. Is okay? Good. Yeah. See you on Wednesday 10. Okay, bye. Bye, guys.
Bye, sir.
Yeah.
Okay, thanks.
Bye, sir. See you.